Okay, here we go. Hi, welcome to the next lecture of Physics X, Extraordinary Concepts in Physics. Today we're doing some really crazy stuff, some paradoxes in special relativity. The title of the lecture is Special Relativity 2, which means there was one you missed, so you should go back up top and click on the other one. And that will give you some basics, and now we're into some strange paradoxes. And please stay tuned for the next one, to Special Relativity 3, because that will be even harder paradoxes. So this is some of the strangest stuff around. It's really strange stuff. And it's fun, too, because you think that reality is really this way. So as I said, this is Physics X. In this series of lectures, I will be covering what I believe to be some of the coolest fundamental concepts in physics, some of which are really very strange. This is actually a course that's being taught for credit at Michigan Tech. There is a studio audience here in front of me. This is aimed at Michigan Tech at upper level physics majors. It's supposed to be light on math but heavy on concepts, trying to get right to the fundamental concepts. Anyone, anywhere is welcome to watch this, though. So if you're just surfing through the internet and you found this, welcome. That's fine. You can just choose any lecture you want, any bunch of lectures. There's no textbook required. I'm trying to teach this so that there is no book. My links are all freely available on the web, and they're also mostly Wikipedia links. And Wikipedia, I think, is pretty strong in this area. So I'll be giving this slide every lecture until you're really annoyed. Okay, so special relativity. This time we're going to move into something called the Doppler effect. Now, you can get the Doppler effect without special relativity. If you just have a train moving toward you, you will notice that the train whistle when it's moving toward you is higher pitched. Then it hits you, and then things turn black for a while, and then when it's moving away from you, then it's much lower pitched. So the same thing is true with light. So if someone is standing and holding a flashlight and pointing this green flashlight toward you, for instance, then you look and say, oh, that's a nice green flashlight. But then they suddenly start running toward you very quickly. And you notice that, first of all, they're running toward you very quickly. So you maybe should figure out what's wrong. Second, you notice that the flashlight has turned blue. Those photons that you were so proud of, so familiar with being red, have turned blue. Then they pass you, because it turns out they were something else, but they point the flashlight back at you. Now you look at the flashlight and you notice that those photons are not blue, they're not even green, they're red. So that's redshift. When it's moving toward you, it's called blue shift. And when it's moving away from you, it's called redshift. And it's most prominent, I guess, when you start in the middle of the spectrum in green. There are other things. The Doppler effect is actually dominant in what you would see in special relativity. If something moves toward you, it not only appears more blue, but it appears elongated. And when it moves away from you, it appears contracted. So there's a famous series of stories written by famous physicists called Mr. Tompkins in Wonderland, or Mr. Tompkins in this and Mr. Tompkins in that. And it was written by George Gamow, who's an excellent physicist. However, in my opinion, and I read this when I was an undergraduate, and it began to trouble me then, but I only really understood why later. Mr. Tompkins is this guy who goes to this lecture and these series of stories, and then he falls asleep during the lecture, and he dreams he's in some world where in the special relativity world, the speed of light is much less than the very fast speed it is now. It's only a few meters per second, maybe. And he also dreams he's in quantum worlds. But in the special relativity world, he doesn't see, apparently, Doppler effects. When things come toward him, the story describes things only as Lorentz contracted, when actually the dominant thing would be when something comes toward you, and especially when they're moving very fast, they actually appear longer. That's the dominant effect. And when they go away from you, so they would appear different colors too, but that's ignored. So you now read Mr. Tompkins, which is very interesting stories with a grain of salt. And I was hoping that somebody would rewrite it, and so they would have the revised Mr. Tompkins stories. And I was very happy to hear that actually a couple years ago somebody did rewrite it. And I ordered the book, and they didn't change much of the physics. So someday, someone out there, please rewrite it to include Doppler effects. Okay, one of the more interesting Doppler effects is transverse. It turns out in special relativity, in our universe, that you don't have to be moving toward someone or away from someone to get a Doppler type effect. In fact, there's a Doppler effect if they move perfectly parallel to you. then they still appear. That might be considered the true Lorentz contraction. They still appear somewhat more red if they're going around you in a circle, their flashlight still appears more red. The transverse Doppler effect is there, and that is a completely relativistic effect. You don't expect that in classical physics. Aberrational effect. Oh, so this is interesting too. So let's say you're driving down the street in front of you, and you see stars in front of you. If you drive fast enough, so fast the police can't bother you, you notice several things. The road appears to narrow in front of you, and the stars that were in front of you, so if you're zipping this way, the stars that were in front of you appear to move together. They become closer together. So the world, the universe, bunches in front of you when you move really, really fast, and that is an aberrational effect, apart from all kinds of color effects. So let's put this into a movie that was visible on Wikipedia. So here you are, you're this object there, and as you move really quickly, you notice that things in front of you turn more and more blue and more bunched together. And things behind you turn more and more red and more spread apart. And that's the combined effect of the aberrational effects and the Doppler effect. That's really the way the universe works. So how do we know this? Well, you can do this in the laboratory to some degree, and so there is real laboratory measurements that confirm this. Special relativity is right. But one dramatic way of seeing this is something called the microwave background. Billions of years ago, photons broke away from electrons and the rest and flew free through the universe and came to us. So there was so we were here, and there's this last scattering surface around us. However, it turns out we're moving with respect to the microwave background radiation. And so indeed, the point we're moving to is about here, and the point we're moving away from is here, and we see all of this on the microwave background. The microwave background appears slightly hotter in the direction we're moving, and slightly colder in the direction we're moving away from. So it works even on the largest scales, even on the most distant scales. Okay. Now we get to play a concept test, what to do. So let's say you had a bunch of blinking lights. This is another, I like to go to the fundamental experiments of special relativity, because that's where I learned the paradoxical experiments, because that's where I learned the most. So let's say you have a bunch of lights that are blinking. Here's one, and here's one. And now this light blinks, and I might have it backwards from what it says there. This light blinks, and then this light blinks. You can consider it to be a wavefront. Let's say there was even another one. This one first, this one blinks second, this one blinks third, this one blinks fourth, this one blinks fifth, and you can just keep going. And it appears that there is a wavefront moving down that set of blinking lights. Is there a maximum speed for that wavefront? And so you can contemplate that. Think about that for a bit. Stop the video if you're thinking about it. And now start it again. Well, here's the answer, and the answer is the blinking sequence can move faster than the speed of light. So everyone is so fond of saying, oh, nothing can move faster than the speed of light, but things can appear to move faster than the speed of light. They can. And the blinking light sequence, sometimes called the Christmas light sequence, it can do that. So sometimes if you just watch Christmas lights, they blink in different patterns. Yeah, it can appear that there's a pattern moving faster than light. However, nothing is being communicated faster than c. That's really what the maximum speed limit is about. Observers elsewhere looking at the blinking light pattern, they might see different lights go on first. They might not see a superluminal wave move down the blinking lights. They might see something completely different. And as I said, you can't use this to communicate. You can sit around and think of ways to try to blink lights so that you can communicate from one point to the next, but you can't. You can't communicate faster than c. Okay. Here's another one. You take a flashlight and you have a dome, and you shine your flashlight here so that it illuminates a spot on this part of the dome. Then you take your flashlight and you swing it around. And so the spot moves on the dome all the way to here. And let's say you do that in a second. Okay? Now, let's say that someone tells you that that dome wasn't close by. That dome was a light year away. Did this flashlight beam on the dome, did the beam move on the dome faster than the speed of light? Think about that. Is it slower than c? Did it move on the dome c? Is it constrained to move at c? Did it move faster than c? Or did it move 5 times the square root of alpha minus 2 gamma? Thinking about that, please pause the video. Here you go. Faster than c. Once again, another example. This speed limit that can't be broken is apparently broken again. You took your flashlight and you moved it. And when you move your flashlight on the wall, the spot on the wall is not constrained to be slower than the speed of light. However, it's not a physical thing, really, the spot. You can't use it to communicate. You can't tell someone on the left, the person on the left cannot tell someone on the right something faster than the speed of light. And if you wanted to communicate to them, the time it takes for the light to go from, so if you're here, and you want to communicate here, this light still takes c to get there, and then it still takes c to get here. So you can't communicate faster than c, but this thing can swing around faster. Okay. The last thing is that we actually see things that appear to move faster than c on the sky. And one clear example of this is quasars in the distant universe. When a quasar emits a blob that moves relativistically, which means near the speed of light, and somewhat close to our line of sight, then you can show, by using triangles like this, that it will appear to move on the sky. You know its distance, and you say, well, given that distance, it can only move this fast in, if it was moving at the speed of c, it can only move this much in a year. But then it moves this much. But that's because it's slightly moving toward you. And so things can appear to move on the sky faster than the speed of light, but that blob that left that quasar, it is not moving faster than c. c is the speed limit. So here we've seen some paradoxes of things that appear to be moving FTL faster than light, but are not. Next time we're going to get into some really strange paradoxes that I consider to be significantly harder. But for this time, I will sign off with please keep Schrodinger away from your cat.